general relativity, step by step. I've been talking about geodesics near black holes, and I've come up with this, Euler has come up with this rather nice expression here that's constant if this condition here, df dt, is equal to 0. What I'm going to do now is to consider g alpha beta. I'm going to consider the arc length in relativity, x dot alpha, x dot beta, where a dot equals differentiation with respect to proper time. I'm going to also require that the d by dt of g alpha beta equals 0, so it's a steady field. And of course this condition here is effectively that condition there. Now if that's the case, oh yes, and the other thing I need to point out is that these are all dots. These are x dot alpha and x dot beta. There's no x alpha in there, it's all x dot alpha and x dot beta. So there's no explicit dependence upon x, which basically makes my life a lot easier. So what I'm going to say here is that f minus, just from here, I'll just change the notation a little bit, alpha dot. You see I've got a subscript I and I'm going to write a superscript alpha instead, and I'm going to replace the dash with a dot just because I can. Die x dot alpha of g. Now I'm going to run out of indices here, aren't I? I'll just write them in, x dot alpha, x dot beta. But I'm going to delete that alpha and call it alpha beta gamma equals a constant. Okay, so that tells me that g alpha beta x dot alpha x dot beta minus x dot gamma times differentiating this lot with respect to gamma. It's quite a difficult thing to do, but I'll try anyway. 2g, that gamma is differentiating there. I may as well call it a beta again, but it's not the same beta, it's an umbral index, so I can call it what I like. That's summed with respect to beta. Yes, that's the result. That's the result. Equals a constant. You'll see how it's quite tricky but very, very rewarding to keep track of what's summed and what's not summed. The Einstein summation convention, as I've said a few times now, is the most profound and suggestive piece of insight. It's such a clever thing. You'll see that I can just differentiate this thing here by sight. Even though we're commuting over alphas, it's also quite difficult. So that's g alpha beta x dot alpha x dot beta minus 2g gamma beta for that term there, x dot beta, and then I'll put this one at the end, x dot gamma, equals a constant. And of course these are proportional. That thing and this thing here are the same thing. So I may as well say that g alpha beta x dot alpha x dot beta equals a constant. And of course that's just the metric tensor, that's just the arc length. I may as well set it equal to 1. G alpha beta x dot alpha x dot beta equals 1 along a non-null, I guess it is, non-null geodesic. Quite a fantastic result that. So what have we done? Let's just go through what we've done in this and the previous screencast. We're going back here to the Euler-Lagrange equations. I'm doing some clever jiggery-pokery with expanding this function f in terms of its three components to get the fact that this is equal to a constant. And then what I'm doing is the function f that I'm considering is just the arc length here, and of course that arc length should be an extremum because a geodesic is a straight, well, it's a geodesic, but it's like a straight line and it's an extreme path. So what I'm doing is I'm fooling around with this constant of integration here to see if I can tie it down, and it's got this beautiful simple form here. I'm going to pinch in a bit and write it out again. G alpha beta x dot alpha x dot beta equals 1. And that's nice and simple. And as we'll see, when we evaluate the geodesic equations in the Schwarzschild coordinates, we'll see that it's a bit of a pain, and we'll use this nice simple result to help us do the algebra a bit more easily. So I'm going to stop there. Stop.